cuspy. If one likes the cuspy dark matter, halos, so you are going to convince us why they are not there. Okay, good.
Okay, hello, so good afternoon. So indeed, I think for people that are interested in indirect detection, the best news would be that there was clear evidence for cuspy dark matter, very cuspy dark matter. But indeed, I will not talk about that, but I would, well, I'm from Vitória, as I told you. If you let me, I'll just flash on another work of mine, but at least this one has better news for people that work in direct detection, that there is something to be detected. This is just because I was being invited for some, thanks, for some, no, I prefer this one, if it's possible. Ah, okay, sorry. Ah, okay, so. Hello, hello. Okay, thanks. Can you hear? Okay, so I was giving some talks about this other paper of mine, and then when I was invited to this one, Farinaldo told me, it should be nice to talk about that issue on cuspies and cores. So this previous work of mine, just briefly, just this slide here, but just that it's common. It's not uncommon to hear that the problem of MOND is that it only works on galaxies. Actually, I remember of a talk of Graciela with a previous talk that I remember she talked something about that, and then later I talked to her, not this time, in another talk of her. But the point of this speech is exactly to say, well, even if you only consider the galaxies, only consider field galaxies, MOND still there is problems. So there are some people that work on MOND that say, oh, at cosmology you have problems, but MOND has to be extended to work in cosmology, but these works are ours is just telling that there is no way, because even in galaxy you have problems. So the point that the MOND depends on the existence of fundamental acceleration. In our work is exactly to say no. This fundamental acceleration that you found in the same data set that was recently used to support MOND, the same data set actually shows that there cannot be a fundamental acceleration. So MOND still has something interesting because there is some interesting correlation that you can find in MOND. There's some interesting idea that appeared from people thinking as if MOND was real. But at least from my perspective, it's nothing but a useful correlation. Likewise, Tully-Fisher is a very useful correlation, but no one tells that. But Tully-Fisher is Tully-Fisher. It's not a fundamental gravity law. Okay, just this one. If someone else would like to talk more about MOND or this paper, it will be a pleasure for me. Oh, sorry, the other way around. Okay, this one. So okay, I will talk here. I'll talk about another work of mine, which is I told you it's centered on the cusp and core issue. This paper here we developed a new estimator for this issue about cusp core. I will also talk about this inner mass deficit. It's related to this cusp core issue. And it's very common to say that only dwarf galaxies suffer from this cuspy core issue. And there are some models that being proposed that change the profile for dwarf galaxies, but do nothing for higher mass galaxies. What we are talking in this paper is exactly that you should take care of that because there is still some systematics. There's not so big difference in large galaxies, but there is still systematic that do not support the cusp in large galaxies. I went in detail on this. And why it has anything to do with, and why it has anything to do with this stellar mass here. Is it working? I cannot see, okay, here. Why this correlation with the stellar mass? And we find that the Burkert profile, which is a phenomenological profile, which is a core profile, and so was proposed only on phenomenological grounds. For some reason, it has a better overall agreement with these galaxies. I didn't say that we have many talks here from people from particle fields. Just to be clear, I'm not from the particle side. Okay, just introduction here to the cusp core issue. it's interesting that it has a long history, and during this history, it has been changing. If you go to the literature, you can find many papers that say now the cusp core issue is solved. There are many papers that tell that, because the point that as time passes, the issue was changing. What is the essential point of the cusp core? For instance, currently, it's common to relate it to a diversity problem and an inner mass deficit instead of a universal slope issue. There are many papers arguing that the problem that the simulation does not tell you that there is a universal slope issue. The situation is more complex than that. But still, there is something that is peculiar, very peculiar about that. For instance, this is just a paper, one of the many papers that talks about this issue. In which you see here, this is the rotation curve of observational data. And if you use this phenomenological profile called Burkert, it fits well. And if you use this Navarro-Frank-White profile that comes from dark matter-only simulations, it's clear that it's very different results. More recent analysis, this from a group that work on simulation. We also include Navarro-Frank-White in this paper here. You can find that that it's still difficult to find this correspondence with the observational data. Here you have two rotation curves. This is the rotation curve with dark matter only, this DMO here, dark matter only. So with dark matter only, you can say, well, perhaps we are not finding this agreement with observation because you are only a simulation that has only dark matter. There is no baryons in it. But also some hydrodynamic simulations include baryons. Also, in this case here, they cannot find a rotation curve that corresponds to what's observed. That if the problem happens only with this galaxy, that would be just a statistical, no important statistical issue. But the point that there are many galaxies that behave just like this one. What could be behind this issue? What could be the cause, etc.? Well, one of the things that people are trying to how to explain this for a long time is telling that, well, perhaps this has something to do with observational data reduction. Actually, it's not that trivial for you to observe a bidimensional galaxy and interpret its rotation curve. It's not something so trivial. There are some subtleties, especially at the center of the galaxy. So perhaps the answer will rely on reanalyzing the observational data. Perhaps there's some systematic that was introduced. But this is something, what is clear, that's not something obvious, because people are looking to this for a long time, and some of the initial possibilities are now considered that are not cannot be alone the source of explanation. Another possibility is baryonic feedback, because the first, for instance, the Navarro-Frank-White halo, it is derived assuming dark matter only simulation. Perhaps it could be changed significantly if you use baryonic matter. And there are some papers that talk about this, the stellar supernova feedback. Perhaps they could change somehow this out. That is, most of the matter is in the dark matter, but stellars, the dynamics in the center of the gas, the stellar component is significant at the center of the galaxy. So perhaps if you have, in particular, supernova explosions, so you have so you disseminate the baryons, and this dissemination could drag at least part of the dark matter. This is one of the mechanisms behind the stellar supernova feedback. And also, which many people also talk here, actually had a talk today, also comments on this, that could be also physics beyond the CDM. Perhaps the halo itself, the Navarro-Frank-White halo, for instance, it can assume a cold dark matter. Perhaps if you have, for instance, self-interacting dark matter, then you have another dark matter halo, and then you have barrier agreement. Well, the point that the core-cusp issue, for some people say, oh, this is just a small detail. In some sense, it's a small detail, because indeed, the standard cosmological model can predict many things, and this is working well. But the point that this is a very problem that is standing for a long time, and the solution not clear. Perhaps it will serve in the end as a window either to add new dark matter physics, or at least improve the model of baryonic astrophysics, which is also very important. If you better understand how how a population of stars can affect dark matter, etc., and many details of astrophysics. That's also important very well, as well. So this is the Navarro-Finquite halo. It is a simulations find with the point that simulations find many halos that behave similar to it. It's not currently the best analytical estimation that we have for dark matter halos or dark matter only simulation. The best one is the ANASO profile, but the ANASO profile has 3 parameters, and actually as people that work on simulations, which includes Navarro-Finquite, also comes that the ANASO is not that different from Navarro-Finquite. They are very close among themselves. And it also has this problem that it needs an additional parameter. Well, and also this 2 parameters here is also simulation indicator correlation between them. There is some papers that claim a very strong problem with Navarro-Finquite halo because they use a 1 parameter Navarro-Finquite. 1 parameter Navarro-Finquite means the following, that you use a correlation to express 1 parameter as a function of the other. This should be done with care because the simulation does not say that there is 1 parameter. There are 2 parameters and they have a correlation. Just this. Not that you can write one and the function to the other. So when you see papers talk about this 1 parameter Navarro-Finquite halo, it's not wrong, but it's something that should take with care. Many galaxy data have tensions with such correlation. There are also many papers comment on that although this correlation appear naturally in simulations, not all. There are many galaxy data that have some conflicts with this type of correlation. Okay. So one of the possibilities is that baryonic feedback could improve this correlation. That's one of the possibilities. Another halo is the Burkert profile. This halo does not come from simulation. It's an halo that was proposed on phenomenological grounds. It has a core in the sense that the slope of the logarithmic slope of this halo here is 0 at the center. So that's why it's called a core. There is no divergence here of this halo at the center. And at a large radius, it decays with the cubic R. Just like Finquite halo. That is, it's just like an NFW halo, but at the center, there is no divergence on the density is constant. It's given by rho 0. And it has a good phenomenological success, especially for dwarf galaxies. This is very easy to find. There are many papers here, and just cite one, but there are many others that talk about the advantages of Burkert profile in regard to the Burkert profile in regard to NFW profile applied to dwarf galaxies. There are some ways to. There are some papers that you can find also in the literature talking about how to generate a core from a cusp. That is, this dark matter simulations only generate this cusp, and there's this with observational data. Perhaps baryonic physics can change from a cusp to a core. There are some papers on that. In particular, there are some hydrodynamic simulations that telling exactly that's possible, and it comes from stellar feedback. These are 2 examples here of hydrodynamic simulations in which they found a correlation between the stellar mass of the galaxy and the slope of the central slope of the dark matter profile. This alpha here is the central slope. Here, in this case, here, this axis here is the stellar mass divided by the halo mass. You can also, from the simulation, you can also convert this in a stellar mass on dependence. Likewise, this one shows here. So here you have, depend on the mass of the stellar mass of the galaxy, you can find what would be its internal slope value. So for some galaxies, there will be a large change on the slope. For others, there will be no big change. It will be especially sensible in this range here, 10 to the 8 solar mass. Galaxies with the stellar mass about 10 to the 8, these are most of the dwarf galaxies, the disk dwarf galaxies are here. Just to compare, the Milky Way is here, 10 to the 10. And well, this approach here led to a modified halo profile. One of them that became, I would say, very popular is this profile. which is, it has 3 constants here on the power law: gamma, alpha, beta, and these parameters here are given as a function of this ratio between the stellar mass and the halo mass. It's possible to fit this. It's not as easy as NFW halo, but it's possible to fit. There is one paper that does this fit, and they did find a better agreement with observation using this halo here, this DC14, than NFW halo. Note that both of them, after you fix this value here, both of these halos here are 2-parameter halos, both the NFW and the center profile. Both depend on OS and RS. Okay. So just okay. And there is one thing that happens if you can just test here that if you put a stellar mass about 10 to the 10, which would be more or less the order of the Milky Way, this profile, the C14 profile, just becomes an NFW profile. Okay, one thing that we would like to address here in this paper of ours is different way to test if there is a cusp or if there is not. Actually, likewise, some papers of Navarro have tells. Sometimes it's very hard to constrain what's the slope of the halo. This is something that's very hard to constrain both from the observational side and from the simulation side. Instead of what they put out is that instead of talking about the slope of the profile, perhaps it's better to talk about the depth on an excess or the depth on a depth on the mass. Because what happens in the end is the rotation curve that is observed. That's what we should compare with. So instead of trying to constrain the slope, it's something sometimes is very hard. You consider the rotation curve itself. But to consider the rotation curve, it means that we are doing a test in a part of the rotation curve to know if there is some excess of the rotation curve or if it's not. So we develop a technique to test this. Not something that the purpose is not to test the complete rotation curve. For sure, you can test the complete rotation curve, but we would like to know if there is some excess of the rotation curve in a part in regard to another part. Excess when you try to fit. If a model has systematically bad fit in a given radius region, this means that this model has a problem. At least it has something that must be explained. If another model has a homogeneous fit for all radius, so it seems more natural than a model that has the same value of chi-square, but at a given radius always has an excess. Just to illustrate how to introduce this approach, well, the first thing is just to illustrate how you have the observational data. You have at each radius, you have a given velocity and then a velocity error. Here's how is defined the chi-square. In general, you have some parameters, and you minimize chi-square. You find the best fit parameters, and this leads to chi-square minimum. Okay, this is just very, very standard. Our approach is inspired on an older work of the Block and Boss, in which they divide the rotation curve in 2 parts. One is called inner, and the other which is called outer part. They differentiate this part, picking the maximum radius and divide by 2. One thing that so they compare how the models fit at the inner part and how the model fit at the outer part. And they found that here they compared the NFW profile with the ISO profile, which is another quarter profile, and they found that especially in the inner part, there is a tendency for the ISO profile, which is a quarter profile, fitting better. Okay, one of the problems that we find with this approach is that this is more or less arbitrary, because this maximum radius is just related with what kind of instrument we are using to observe the galaxy. It's not a distance that is natural of the galaxy. Another approach would be to use chi-square in which you evaluate as 1 kiloparsec, 2 kiloparsec, 3 kiloparsec, etc. That's another. This has also something similar of a problem, because actually these scales are not natural to the galaxy. There there is a natural scale that emerges in a galaxy, which is about 2 kiloparsecs, but it changes from galaxy to galaxy, which is the disk scale length. The disk scale length gives how the surface brightness of the galaxy, of the stellar surface brightness of the galaxy, how it changes with the radius. So different galaxies indeed have different disk scale lengths, but the average value is more or less about 2 kiloparsecs. So instead of using a fixed value of kiloparsecs or the maximum observed radius, we adopted the disk scale length, which since the feedback is expected to be related to the stars, the natural distance scale would be the disk scale length. So use this disk scale length. So it's an emergent. It's emergent. Okay, I told you everything here. So and now so what the quantity that you use to measure to compare different parts of the rotation? How is my time? Okay. Okay, it's there. Okay. Includes ask questions. Okay. Okay. So the idea is just to compare here two chi-square quantities. One of them calculated up to a given radius given by m times the disk scale length. So h is the disk scale length. So m would be a number divided by n, the chi-square up to n times the disk scale length. So if you have, let's say, this approach starts intuitively in the sense that if you have a galaxy that the data is uniformly distributed with the same error bars for all the points, in case you have the ideal set of data, and in case you have an ideal model that's capable of fitting everything very uniformly, you would expect that on average this should be more or less like m over n. That is the ratio here of this 2 chi-square. Well, and indeed you can compute this, assuming that you have this kind of ideal data set, and you can express this as a function of this generalized, regularized, incomplete beta function. And from this, it's possible also to find what is the best ratio of this m and n, such that it improves convergence. We would like to use an estimator that converges the quickest as possible. So using here to estimate the average, we're using the median, not the mean. And if m is equal to 2n, then we find the best case in which everything we need, the only thing that we need, that's the data. We have more data than we have parameters to be fitted. All the other options would be worse than this one. Okay, and this for an ideal data set, but some galaxies are not ideal in the sense that some galaxies, they have naturally more data, more observational data close to the center than farther from the center, or the opposite. Or they have the data points are uniform distributed, but you have larger error bars in the beginning and smaller error bars in the end, or vice versa. So you have some quantities also to compute this, how the data is homogeneously distributed, how the error bars are homogeneously distributed. The quantity zeta 1 here that we introduced, it's essentially a sum of the inverse of the errors, and in the end, the estimator that you look for is this delta chi here. The point is that so we expect that an ideal model should find that on average this delta chi should be close to 0. Here, what the data set that you use, this is the first, this is a compilation of many samples that you used. When you published this paper, I had not yet access to a more recent data that will come soon, which is Spark data. But here we compiled these many samples here and achieved 62 galaxies. For these 62 galaxies, the very first test easy to do. You just fit all these galaxies, find the chi-square, the total chi-square of each, and compare with the stellar mass. And comparing the stellar mass, what do we find? Well, the first thing that is very easy to find, that's from the 62 galaxies, 13 of them fit better with the NFW. All the others fit better with Burkert. But perhaps there is some tendency with the stellar mass. And the answer, yes, there is some tendency, but not as good as expected from the simulations. in the sense that it's possible to see that when you go to higher stellar mass, at some tendency of NFW to fit in better, but this happens only to 10 to the 11 stellar mass, not to the 10 to the 10. 10 to the 10, there is no evidence for that. And recently, this is not published. I did the same thing with the Spark data. For the Spark data, you find essentially the same tendency, in which 10 to the 10 you find no clear evidence, and perhaps above 10 to the 11 you find some evidence for NFW to fit better. For sure, here 10 to the 8 you have much larger evidence for in favor of Burkert, but even for 10 to the 10 there's here no it's not something that an NFW is better. So you have a halo that becomes an NFW, you're not following, it seems that you are not following observational data. But perhaps this is more a thing of to calibrate the simulation, perhaps, because there is this difference of 10 factor. So about the homogeneous of the fits, here for the Burkert one, here for the complete sample. So this 0 here would be the expected for an ideal. This brown line here is what's found for the Burkert case, which is close, and these two regions here show the distribution. 25% of the data is here in this orange part here, and what if 50% of that in this yellow region here? Actually, the errors of the median, each bar here is computed from medians, not from means. From means, you'll be dominated by outliers. Everything is computed with medians. Okay, and if you do and you compare with NFW, we find that NFW has a much lower value for delta chi, which means that it's fitting better for larger radius than inner radius. It fits better in the region up to 2 disk scale lengths than the region up to 1 disk scale length. Just to be clear, as we tell in the beginning of this paper, this is not yet, let's say, a full Bayesian analysis. There is many things to be done here. Our major approach is to introduce a new approach, a new way to quantify this kind of cuspy core without computing directly the slope of the profile, which is, as I told you before, computing the slope is more tricky. Okay, and what if we do subselection of samples such that we pick larger galaxies? Perhaps this conflict here will go away if we pick larger galaxies. For instance, you pick for instance, a sample here in which you only include galaxies with larger mass, only the galaxies with 10 to the 9 or only 10 to the 10. Here's the point that here's the original sample that I showed the plot before. Here's you have the Burkert answer. Here's the NFW answer. The point that once you pick different subsamples that removes the smaller galaxies, the point that the answer is essentially the same. There's no big difference. NFW, for instance, does not become better, perhaps even a little worse. Just now the conclusion, because I'm almost lost out of time. So to review, we find that this Burkert profile fits better than the NFW, even if you consider galaxies with about 10 to the 10 stellar mass. The picture may change at 10 to the 11 because we have less galaxies to test. Perhaps perhaps the essential idea behind the stellar feedback is correct. It's just some issue of calibration, or perhaps a new baryonic effect that was not taken into account. It should be inserted. Also, we find that this NFW profile has a tendency of it better the region between 2 disk scale length and 1 scale length, then the region of 1 disk up to 1 disk scale length. And curious, if you want to select only the large galaxies, this effect does not change. The situation is not improved for NFW. So our results point out that baryonic feedback or CDM models, which only change NFW for dwarf galaxies with stellar mass of 10 to the 8, should explain why a core profile, like a Burkert profile, commonly works for larger galaxies better than NFW. So if you only have a model that only changes for 10 to the 8, you still have some, you may solve the main parts, but why Burkert is still fits better for the large galaxies? What's happened? Perhaps some may say, no, perhaps here you are entering some details of astrophysical nature, some doubts about how to do this calibration correct on the observation rotation curve. Perhaps that is, but the point that there is something that should be explained. So, and I conclude here.
Okay, so we thank Davi for these reasons against the cuspy. So let's see if there are questions.